I'm Emily from Team 1236. I'm one of the team captains. And so the 1276, the green team, is the founder of the FTC Open Alliance, and we saw a lot of interest in all the videos that we had been posting. We were getting a lot of comments on how do you do this. Um, so we decided that we wanted to start off a little knowledge exchange thing. So today we just wanted to do a quick run through of how we did those, the turret and the auto aiming and all that stuff, so that other teams could do it as well. I don't know when we want to end the video.
Okay, so I think to start us off, the plan is to do sort of an overview with the whole group, and then we'll do some breakout rooms to talk about specific ideas related to the project. And what I think I'll do is I'll just start the video playing, and then we can sort of pause it in places and talk about things. And certainly, if anybody has any questions, just ask. This is super informal, so we just want to help. So if you have questions, let us know. But I'm gonna share the video, and we'll see what we want to talk about. So um, okay, can everybody see this? Okay. All right. So
Okay.
I'm going to play it and then I'll just be ready to pause it in certain places. So this is going to go through sort of our process over the last couple weeks. A bunch of it is from the first 30 hours, and then we'll see where we get. Okay.
Emily, I'm gonna go on your side so we can push against each other.
This is from Sunday after kickoff.
Ready?
This is a couple minutes later.
Yeah, we need to get 3 times.
You ready? Did you see that?
Okay, so the first thing we did to work on this problem was we did a physics model in Excel. I'm just going to pause this for a second. So what we did is write some physics equations that we could do some little incremental, almost calculus stuff. And the output we got, so this is in Excel, this little object is our robot. And this is the trajectory of the balls. This is the front edge of the target, and this is the back edge of the target, which is higher. And this, we just, got Excel to draw this for us. And then I'll show you. So this is what the full thing looks like. So on the input side, we can put in an X and a Y distance in feet on the field. And then there's a Z offset based on the height difference between the top of the shooter and the bottom of the goal. And then we have Excel just switching feet into meters for us to do physics in. And then we're doing the Pythagorean theorem to calculate the range based on the X and Y distances. And then we're also calculating how long the ball should be in the air to go that far. Down here, we have some constants that we could tweak. We've got the height of the target, a value for gravity, the RPMs of the motor, and then our desired shoot velocity. And then we have sort of a conversion number to switch the RPMs into a speed. And then on the other side, this is where we're doing all the drawing. So we're looking at all these moments in time and then calculating where we are. And what you can see is as we change values, like our shoot angle or whatever, that then the whole picture changes dynamically to show us what's going on. And we can adjust, our range to target and anything we want. And this is going to give us firing solutions for what the RPMs should be and what the angle should be to hit the target from anywhere on the field. And this is an important step in what we want to do. Our goal is to automate as much of the shooting as possible so that we don't have to think about where we are in the field. Wherever we are, we just hit the shoot button and the robot will shoot the correct trajectory. And modeling the physics of it is an important first step to that. And the first thing we did is do it in Excel because it's quick and easy and gives us a nice visualization of what we're doing. So this is the robot that we made this week to sort of test the idea. Etienne made this base. It's just a fairly standard go build a Mecanum base, and then Josh and some other kids put this turret together. It's not a turret. It's just a shooter. We're using the turnability of the robot to aim, but there is a flywheel in here to hit the ball out. There's a little servo kicker down here to send it in, and then this deflector is on a servo that can move up and down to change the aim. And then let's see, in the front of the robot, there's a better view, I think. You can see, yeah, this is the camera that we put on to look at the April tags. It's just a $40 camera from Amazon. Okay, so this is the setup we did to start testing our physics to build a model with. So obviously this is on our field. The robot's sitting here. This is a meter stick, and this is another meter stick. And these are in here to be references for the trajectories that we're going to shoot. So I'm going to just play this. So once this was all set up, we got a camera over here and we recorded shooting. So that's power, a little more power, a little more power. And then we used a piece of software called Vernier Video Analysis. This is a web-based app. It is not free, but it's not expensive either. Most schools have access to this. So what we did is we uploaded our test videos to this. And the first thing you do in the software is you set a scale, and we're doing that by highlighting the meter stick in the X direction and telling the software that that's a meter stick. And then it can scale all of the pixels on the screen to real world values. Once that's set up, we can go through and advance the movie frame by frame and track the ball through the air. And as you do that here, it's also plotting in real time as you're clicking what the position of the ball is. It's doing the X stuff in red and the Y stuff in purple. And you can see we got a nice constant X speed and then a parabola that we're expecting in the Y direction. And once we have that, we can do the software will get us equations for us. So we can get values for the speed and everything like that. It also gives us a built-in check because we can use the data to calculate the value for gravity. And if the value for gravity is close to 10, then the data is trustworthy. If the value for gravity is not close to 10, then that's a bad video and we're not going to use it. So there's a self-check built into this process. So basically we went through, so here's what we got for that X direction, and this is the Y direction for that first test. And then we simply do it a couple more times. And I have this like sped up so we can just see it happen quickly. So this is a higher power setting. It's important to do a bunch of power settings because the whole point of this process right now is to figure out what launch speed we get as a function of the RPMs that we're using. So James made a function for the robot that would just be allowed to, on the gamepad, switch up and down how much power we were using. percent power. So we went from 80 to 100% power, and then we made curves of all that. Mm. James, you were saying you could do that with FTC dashboard really easy too, right?
The like setting the power, you can also just do that with telemetry. I
Mhm.
just had it outputting whatever the power was.
Mhm. See, I'm just gonna scrub through this. So there's a third one there, but we did several tests of this and got nice lines. Um, okay. Yeah. And then you can see from these error values, the fit's really good. The data is pretty trustworthy. So I'm just going to pause here. So this is the physics ideas that we're using for analyzing those videos. So the computer was telling us the X speed and the Y speed. So we were able to combine those to get the total speed that it was shooting at. And then we could also do a little trigonometry, taking the initial speed in the Y and X and doing the inverse tangent to get the angle we were shooting at. Um, and those equations are also in the Excel model. So what we wanted to do for our check is we know that gravity is 9.8. So we did a percent difference calculation, 9.8 minus the G value from the videos over 9.8 times 100 to just see how off we were in the videos. And here's the data that came out of those videos. So we ran it at 80%, 90%, and 100%. We had X speeds from the computer, Y speeds. We did the Pythagorean theorem to get the total speeds. So that's all good. Now, it should be noted here, we were doing the machine that we were running in these videos was a practice thing with only one roller. Our real robot will have two rollers. You can see even at 100% here, our shooting speed was about 4 meters per second. And I think James and I both independently calculated that to do a full court shot, you need 8 meters per second. So this robot design isn't the final robot. It can't do it. But we were able to get shooting angles and we got values for gravity from the video. One that was a little bit sketchy and then two that were pretty much perfect. But that independent checking is important to make sure you trust the data. So then once we had that data, now we're making a graph here of the power on the x-axis and the shooting speed on the y-axis. And this is an important step because our programmers are going to need to turn the percent power that they use for the robot into a shooting velocity. So when we plot the data from those tests, slow. Okay. And so we'll have to do this process again once we make the final shooter. But our parts for that have mostly come in at this point. So we're going to be able to build that this week. But we can see we got a nice straight line here, which is the relationship between, again, the power that we're shooting at and the speed that we come out at. So, that means that our shooting speed is going to be very predictable, and we can program the robot to do this automatically. The other part of this project is the vision stuff. Yeah. Um, yeah, our student that's an expert on the visiony stuff isn't here yet. He's on a college trip with his parents. He thought he would be able to join the meeting. Apparently, that didn't work. So that's okay. We'll talk about it. This is the equation we got from the um, that last graph, which is linear. So our next step is to, at constant power, vary the deflection angle and see how much we can change our shooting angle. And we want to make a graph like this. What angle do we use? Stuff. So this is the important part. This is one of the motif April tags that's loose that Hamid is holding. And this is from 30 hours. We have on our robot a turret that the kids built and just put a camera on it. And what you can see here, um, so there's a turret with a camera, and it's being told to track the April tag. So the robot's just sitting here, Hamid's moving the tag, but it is keeping it tracking really well.
They put epic dubs.
Now here's a slightly cooler version where we're looking at the stationary tag and moving the robot, but if you keep an eye on this camera, it's always tracking the tag.
Dude, this is like military tracking. Raytheon, call me!
Yeah, how far can we
Yeah, how far forward can we go?
Oh my gosh, it's good.
You can easily
Go further?
And you don't want to go further because the layup robots are going to be up there.
Yeah.
No, like the field ball.
I think it's about, yeah, it's right here. Yeah, so about there.
That's perfect.
So one tile away.
Okay. I'm going to turn this over to James at this point just to talk about a couple of these graphs. James, just I can pause it when you want to. Actually, here, I'll pause it here. What's this, James?
So I ended up getting sick for 30 hours, but I still ended up modeling it without realizing anything which they were doing. But instead of Excel, we're using Desmos for this. And one thought which I was having for this is, will like the angle that the ball enters the zone matter? Like, will it bounce out at certain angles? So the nice thing is with Desmos, you can do a 2-point regression rather than just a single target point. So if it turns out banging it against the back wall makes it fall down faster than just going straight in from the top, you can control that. And another thing is if you have a 2-point regression, you need 2 degrees of freedom, which in this case, you have a power and an angle you're shooting at. So what we have here is I've set up a regression for a parabola to go through 2 points. And what's the camera? It just has a fairly wide field of view. I mean, we're using Articams for that, so it's normally pretty good for that. Also, they're global shutter cameras, so you don't have to worry about motion blur as much. But it's just treated like a standard USB camera. Oh yeah, the other thing is, even though I have a standard regression for this, I can hook up the distance to another variable and take note of the power and the angle needed to achieve that parabola and iterate over that distance to make another set of regressions. It's not an interactive graph, I think it's a video. But I guess in the breakout room, I'll go over, if you click on the regression modeling tab, you can see the graphs of the angles and the speeds which come from this. You can convert those into functions. And since we're using April tags, which have fairly accurate distance readings, we can just take that distance off of it and then plug it into this, and then you have your parabola that you need.
Mm-hmm. Okay, so the other screen capture we grabbed is there's 2 more, James. I want to talk about just general.
So one tile away.
Oh, where'd that go? Okay. That was that one. There, this one. Let's talk about this one too.
So another thing, just as another way of calibrating our cameras, in this case, we have the distance which the camera is giving out versus the distance which it actually is. And the upside of doing it this way over like just standard calibration is then you can graph your error. So since I mean, in this case, I've boosted up by like 100, so that we can actually see it. But if we do this, then we can also factor in the error of our distance from the camera into our calculation, so we know if we're within the tolerance of hitting it into the goal.
And when we were practicing, James and Emily were doing this the other day on the field, and when they were like as far away as they possibly could be, the error was like, I don't know, something like 7 or 8 centimeters, and the width of the target, like looking top down at the goal box, is 45 centimeters. So if we're aiming for the center of the target, there's no way we miss because the error is within that bound. And then I think there was one more graph that we included in this video. Yeah.
So in this case, you can't really see it because it's so zoomed out, but this graph is also taking the data from the previous one and that error which comes from it and creating two parabolas, one that margin of error over and one that margin of error under. But this is very heavily inspired from a seminar we were watching from an FRC team, where they, based on their distance, they take into account their margin of error for each of their subsystems. And this way, like if you're really close to the target, you don't need to have like half a degree of accuracy. You can have like 2 degrees of accuracy and it'll work fine. It increases speed.
I think that was all, yeah, that we put into the general video. I'm gonna stop that share. And so here's what I'm gonna do, just so that everybody has access to this. So I'm gonna actually, in the chat, I'm gonna put a link right now. This is our page on the Open Alliance, and I'm just gonna really quick, actually, I'm gonna share something else right now. Um, I'm gonna share this tab. Can you guys see this? I don't know what that is. This is what I want to share. Okay, so this is that link I gave you takes you to this page on the Open Alliance. This is our list of teams that are signed up, and there's a whole bunch of them. But our team, 12736, these are buttons on the website. This button will take you to our build thread. It's opened up. There's a new post every week, and it's usually got all of the CAD and code updates that we've done that week. This link will take you to our public Onshape document, so you can see like what we're building and how it works. This is a link to our GitHub account. All of the code that is making the April tag stuff work, all the code that's making the physics work is there, and you guys can look at it and do whatever with it. We also have links to the photos and videos that we have shared if you want to see those again. So like, and all the Open Alliance teams share stuff like that, but that link I just put in the chat will get you here in one step, and then you can see all of our stuff. So I want to just ask our guests, does anyone have any general questions about what we've shared so far? This was meant to be just an overview of the problem and our solution. And what we can do is, in a minute or two, I'll open up 3 breakout rooms. There will be a mechanical discussion room that Josh is going to run. And Etienne, you could go in there too. And we'll be happy to show you our turret designs and our shooter designs and talk through our choices for that. And then we're going to have a vision discussion. Our absolute expert on that, Hamid, isn't with us right now, but Emily will go in there. She knows a lot of it, and she can help with that. And then we'll also have a physics discussion, and James will go in there and talk about his Desmos models and how they work and how you can use them. And James, I think it's also okay to share the links to that Desmos stuff with people as well. Okay. But before we go into breakout rooms, does anyone have any general questions about this problem or the process? We will absolutely post the recording as well.
They mean where?
Where will you post it? So I think what we'll do is we'll put it on our social media stuff. We'll also put it into our build thread on Chief Delphi. So if you follow this link, you can get to our build thread on Chief Delphi and the video will be there. Um, uh, James, do you want to talk a little bit just about the camera that we're using? I know you mentioned it quickly, but do you want to mention it again?
Yeah, so we're using an Articam's black and white global shutter camera. Um, can
Yeah, I'll put the link to it in the chat while you're talking about it.
well, it's a Limelight 3A camera. They only recommend it. So the thing is, there's like two sets of libraries you can use. One of them is like, I believe you can find it in the examples under like concept April tag. This works with any USB camera. So oddly enough, the reason why we're using Articams is this is what we use for April tag localization for FRC. And they're global shutter, which means they have very little motion blur. Limelight 3A, I believe, is rolling shutter. But the upside of Limelight 3A is A, it has like the automatic localization libraries, like you import a tag map, and then you just do like limelight.get position, and it'll give you your position on the field. Articams, you just plug them in. The libraries are a little bit weirder, but if all you want is distance off of them, then I'd recommend them.
Mhm. Here, I'm
Um,
putting in the chat right now. This is the camera that we're using. It's $40 on Amazon, and it's working great for us so far.
any other camera questions or?
Okay. All right. I'm going to open up the breakout rooms, and then people can sort of split up. The rooms are labeled a mechanical room, a physics room, and a vision room. I'm hoping that everyone sort of unmutes themselves and just talks to each other for a while. We'll probably do, it's 10:30. We'll probably do about 25 minutes or so in the breakout rooms, and then we'll come back to the main room, have a wrap-up discussion, and see if there's anything that's like, the group wants to talk about. When you said you're going to add another motor and a wheel, did you mean on the flywheel? So yeah, that we'll talk about that in the breakout room, but probably two axles. So we can have a bottom spin and a top spin, but I think you'll see that in the CAD that the kids are working on. Okay, I'm going to open up the rooms, and y'all can join a room. Okay. Okay. All right. So, I hope you all found this useful. Uh, we did make sure you grab those links I put in the chat for where to find our CAD and code on the Open Alliance Teams page. And if you want to investigate that camera that we're using, I have the link for that in the chat as well. Does anybody have any final questions or thoughts that they want to share with the group? Was this useful?
Yes, very. Thank you.
Sure, absolutely. Okay. Well, thanks for joining us this morning. I really appreciate y'all spending some time with us. And if you have any questions, my team is very friendly. Feel free to reach out to us. You can write us comments in our build thread. That's an easy way to talk to us. Or you can find us, on various social media things, but the build thread's probably the best place. And I'll just put in a quick plug too. All of the Open Alliance teams are really friendly and nice. I would encourage you to join that group. It's a great way to be a part of the bigger community, and honestly, it's a great way to do outreach too, like this of putting out what you're doing out there in the world for other people to learn from is a great thing. So thanks again for joining us this morning, and I hope you have a good season and enjoy the rest of your weekend. Thanks, everybody.